Since thousands of years ago, humans have always taken interest in the study of shapes. From Pythagoras to Descartes to Gauss, geometry is one of the oldest and most influential branches of mathematics. And just like geometry, there are three special problems which will always remain timeless. It goes like this. Given a compass and a ruler without any markings on it, is it possible to split a given angle into three equal parts, produce a cube with twice the volume of another, and/or construct a square with the same area of a circle? These three problems can be summarized in a way that rolls off the tongue quite nicely. Is it possible to trisect the angle, double the cube, and square the circle? These problems, though easy to state, are actually quite difficult when you really get into it. I'm sure even the great Greek geometers like Euclid and Pythagoras spent some time on these problems only to discover that it was a waste of their time, and they should instead spend it by trying to construct a pentagon or something. Now, you might ask yourself, why would this be so hard? It sounds pretty easy to me. And you would be right, they do sound pretty easy. So easy, in fact, that a third grader might even attempt it. But I can assure you, you too would only waste your time trying to come up with a solution. And spoiler alert, that's because there is none. In fact, it has long been proven that a solution to any of these problems does not exist. But before we really get into these three interesting problems, I want to make sure that we're all on the same page when it comes to geometry and constructions. In a construction, we can only use a compass and a straight edge to make a figure or shape. With a compass, you can make circles, and with a straight edge, you can make straight lines, and that's it. You might think this is pretty limited, but these tools are actually quite powerful. If we're given a unit segment, then we, through geometry, are physically able to add, subtract, multiply, divide, and even take square roots of rational numbers. This is important because it allows us to transform a difficult geometrical problem into an algebraic problem, giving us more to work with. An important distinction in these constructions is that we're not given a ruler, but instead a straight edge, something without markings. You might be excited to know that if we did have a ruler, all of these problems would have easy, simple solutions. But that's not the case here, and it's one of the reasons these problems are so hard. But enough of that. Let's get into our first problem, trisecting the angle. I think we can all agree that a 90-degree angle can easily be trisected. Just construct an equilateral triangle to see why. However, what we want to show is that not every angle can be trisected. To demonstrate this, all we have to do is find at least one angle that can't be trisected with compass and straight edge. To start, I'll demonstrate how we can construct an arbitrary angle in the familiar Cartesian plane. Given some angle theta, all you need to do to construct it is construct the cosine of theta and the sine of theta, as these are just the x and y coordinates of the angle. So if cosine of theta is constructible, it follows that the angle is constructible too, and vice versa. Now suppose we have a 60-degree angle. We want to find out whether or not we can trisect it. If we can trisect a 60-degree angle, then that means that we can construct a 20-degree angle, and in turn, the number cosine at 20 degrees is constructible. There's a handy trigonometric formula which, at the moment, looks unnecessary and strange, but in the end helps us solve our problem. If we let theta equal 20 degrees and substitute x for cosine of 20 degrees, then what we're left with is a polynomial with cosine of 20 degrees as a root. Furthermore, I'll substitute 2x for y, which will help us out in a bit. At this point, you might be asking yourself where we go from here. This is where abstract algebra comes in. Basically, any root to our polynomial is not constructible if we can't factor it with rational numbers, and its degree is not a power of 2. To check whether this polynomial is factorable with rational numbers, all we have to do is use the rational root theorem. Our constant term is -1, and our leading coefficient is +1, So our only possible roots are positive 1 and negative 1. Some quick mental math shows that neither of these work, so this polynomial is not factorable over the rationals. Also, notice that 3 is not a power of 2, so finally we can conclude that cosine of 20 degrees is not constructible. But this means that a 20-degree angle is not constructible either, so a 60-degree angle cannot be trisected. Just for a moment, let's peek into the world of ruler and compass constructions. If we're given an angle, then the problem of angle trisection has an easy, simple solution. Say we're given an angle, which I'll call AOB. First, drop a perpendicular from A to meet OB at C. Next, draw a parallel line to OB passing through A. Now, using a ruler, construct line OE such that DF and FE are equal in length to OA. For brevity, I'll say OA has length little a. Next, find G, the midpoint of AE, such that AG and GE have length little b. If we connect points G and F and A and F, notice that by side angle side, we have two congruent triangles, EFG and AFG. As a consequence, side AF also has length A. Now, remember when we constructed the parallel line AE? By alternate interior angles, we know that angle DOC, which I'll call alpha, is congruent to angle GEF, which in turn is congruent to angle GAF, again by congruent triangles. Next, through a bit of algebra, we find that angle AFO is secretly 2 alpha, and as triangle AOF is isosceles, that means that angle AOD is also 2 alpha. Finally, we can bisect angle AOD to get 2 alphas, and thus the trisection of angle AOB is complete. Let's move on to our second problem, duplicating the cube. This one actually isn't too bad. To recall, say we have some cube. We want to show that it is not possible to construct a cube with twice the volume of our original cube. For this problem, we'll just focus on the construction of the sides of our cubes, as it's pretty straightforward to get the rest of the cube. Let the side of our smaller cube be A, and let the side of our bigger cube be B. What we want is for B cubed to be the same as 2 times A cubed. This means that B is equal to the cube root of 2 times A. To make the math a bit easier, let's let A equal 1. Then B is just the cube root of 2. Now, our problem of duplicating the cube boils down to whether or not the cube root of 2 is constructible. Similarly as before, let's consider the equation x cubed minus 2 equals 0. The cube root of 2 is clearly a root of this equation. So in order to determine whether it's constructible, we have to figure out whether or not we can factor this polynomial over the rationals. Another application of the rational root theorem quickly shows us that we can't do this. And as the degree of our polynomial isn't a power of 2, it follows that the cube root of 2 is not constructible as well. Finally, to wrap it up, let's look at my favorite problem, squaring the circle. Firstly, I just want to say that this problem in particular is quite infamous for its difficulty. The proof for its impossibility took more than 2,000 years. Even Dante of Dante's Inferno and Lewis Carroll of Alice's Adventures in Wonderland knew of the problem, and today it's seen as a metaphor for attempting the impossible. Suppose we have some circle with radius r. We know that its area is just pi times the radius squared. And suppose we have a square with side length s, then its area is simply s squared. What we want is for these two areas to be the same. So, through a bit of algebra, we can find that s has to be equal to r times the square root of pi. Now keep in mind, r could be any number, so to make the math a bit easier, let's let it be 1. What we get is s is equal to the square root of pi. Again, we must ask ourselves, is the square root of pi constructible? I don't think it's much of a stretch to say that if the square root of pi is constructible, then pi must be constructible too. However, there's a remarkable result of number theory that dates back to Linneman of the 19th century, which says otherwise. Essentially, Linneman proved that pi is transcendental, which implies that pi cannot be constructible. Now that you're an experienced geometer, you might wonder why mathematicians decide to use their time by trying to solve these problems in the first place. After all, it's not like your barista is ever going to ask you to square a circle, so why bother? Well, it all comes down to a common theme that frequently comes across any seemingly difficult math problem: abstraction. By making a problem more abstract, we were able to figure out a solution. And who knows? The solution to a very, very difficult and important problem, such as the Riemann hypothesis, might come from an unexpected area of mathematics. Also, these problems are fun, so why not indulge in some interesting mathematics? Thanks for watching, and stay safe in your adventures throughout math.